Welcome to the deep dive. Imagine for a moment a world where your most secure data, encrypted with state-of-the-art algorithms, could be stolen. Not by cracking complex mathematical codes, but just by listening to the faint electrical hum of your device. It sounds like something out of a spy thriller, right?
hmm
We often envision digital security as this, well, impenetrable fortress guarded by layers of complex algorithms and secret keys. But what if the fortress walls themselves are subtly leaking information, like a whisper in the wind that a determined adversary can pick up?
It's a striking image, yeah, but it captures the essence of a very real and frankly rapidly evolving threat. Cryptographic algorithms, they're mathematically designed to be incredibly strong, making brute force attacks, simply guessing the key practically impossible. They're built on the premise that without that secret key, the computational effort to break them is, well, astronomically high, often exceeding the capabilities of, like all computers on Earth combined. But what we're diving into today is how adversaries are sidestepping these mathematical strengths entirely by exploiting unintended physical side channel leakages, things coming from the actual implementation of these algorithms on, say, embedded hardware. It's about listening to the physical world of the hardware, not just the logical world of the code, and finding vulnerabilities that are literally invisible to our traditional security models.
Okay, and today we're taking a deep dive into some truly groundbreaking research that pushes the boundaries of this threat in a pretty significant way. We're talking about a study titled X-DeepSCA, Cross-Device Deep Learning Side Channel Attack.
hmm
And this isn't just theoretical, right? This research reveals how advanced artificial intelligence can break embedded encryption devices faster, more effectively than ever before, and crucially, even across different devices. Devices the attacker might not have direct knowledge of beforehand. That sounds like a big deal.
It really is. So our mission for this deep dive is to pull back the curtain on this cutting-edge area of cybersecurity, to give you a shortcut to being well-informed. You'll understand what side channel attacks are, why they've historically been so challenging to perform across different devices, and how this new deep learning approach, X-DeepSCA, has overcome those very significant obstacles. This innovation dramatically increases the threat surface for the embedded devices we rely on every single day. Think about smart home gadgets, our cars, medical devices. Get ready to have your understanding of digital security, well, profoundly shifted. Hashtag tag the invisible threat. What are side channel attacks?
Okay, so let's start with the baseline. The bedrock of modern digital trust is cryptography. We rely on these algorithms to ensure data integrity, confidentiality, and virtually everything we do online. Banking, secure messages, you name it. The entire security model is based on keeping a short, secret key secure, right? Without that key, a brute force attack is supposed to be statistically negligible in its success rate. You'd need more computing power than currently exists to guess a truly strong key.
That's precisely right, absolutely. Take AES 128, for example. It's a widely used encryption standard, and it's also the specific target in this research we're looking at. Its mathematical security is incredibly robust. The sheer number of possible 128-bit keys is roughly 3.4 times 10 to the power of 38. Just a massive number. It makes guessing virtually impossible, even with the most powerful supercomputers working for billions of years. This computational advantage is what allows secure communication and data storage to happen without us constantly worrying that our encrypted data could be instantly decrypted by some clever attacker. It's the foundational assumption of modern digital trust.
But then we encounter this concept of side channel analysis, or SCA. That term itself sounds a little covert. You're telling me it doesn't try to break the mathematical algorithm itself. So if we stick with our safe analogy, it's like listening to the subtle sounds a safe makes as someone tries to open it. Rather than trying to guess the combination directly, you're picking up on subtle clues from the physical act itself, not the abstract logic.
That's a perfect analogy. Yeah, it cuts right to the core of what SCA is. It's a form of cryptanalytic attack that completely sidesteps the mathematical strength of the algorithm. Instead, it exploits, as you said, unintended side channel leakage. Things emanating from the physical implementation of the cryptographic algorithm on an embedded device. Think of it this way. The mathematical equation for encryption might be perfect, flawless in its design. But when that equation is run on real-world hardware, with electrons flowing, components heating up, operations taking tiny amounts of time, it produces physical side effects. These physical emanations, however subtle they might be, contain information. Information that an adversary can analyze to infer the secret key. It's a fundamental vulnerability that pure mathematics alone can't really predict or prevent because it arises from the real-world physics of computation.
Okay, that makes sense. So what kinds of whispers are we talking about here? What are these different types of physical leakage that a device might inadvertently give off?
Well, there's a whole spectrum of physical signals that can be exploited. And the research paper we're discussing today, X-DeepSCA, it focuses specifically on power consumption. This is one of the most common and potent forms of side channel leakage. As a device performs cryptographic operations, its electrical power usage fluctuates. And it fluctuates in patterns that are subtly dependent on the data being processed, including the secret key. Different operations, or even the same operation with different data, will draw slightly different amounts of current. This creates a unique power signature, a kind of electrical fingerprint. These variations are incredibly small, often in the millivolt or microamp range, but with specialized equipment, they're definitely detectable.
Okay, power consumption. That's the main focus here. But you said there are others.
Well, absolutely. Power consumption is just one avenue. There are other important types too. Electromagnetic radiations. Just like power, devices emit electromagnetic signals during operations. Any current flow generates a magnetic field, right? And these fields fluctuate with the underlying computation. These EM emissions can be picked up by sensitive antennas placed near the device. The advantage of EM radiation is that it can sometimes be more localized, meaning different parts of the chip might have distinct EM signatures, offering potentially even finer granularity for an attacker. Processing time. Timing attacks. This one's fascinating. The exact time an operation takes can sometimes vary based on the secret key or specific data values being processed. For example, if a conditional check takes, say, a few nanoseconds longer when a certain bit of the key is 1 versus 0, that tiny difference can accumulate over many operations and actually reveal information. Even minuscule differences, often totally imperceptible to the user, can be exploited statistically over many, many runs. Cache hits misses. Modern processors use memory caches to speed up access to frequently used data. Observing patterns in how a processor accesses its memory cache, whether it's a hit where the data is already in the fast cache, or a miss where it needs to fetch it from slower main memory, that can also reveal information about secret operations, particularly in scenarios where cryptographic keys are accessed in a data-dependent manner.
Wow, so many different angles.
Exactly. And the crucial common thread here is that none of these directly involve trying to, reverse engineer the encryption algorithm's math. They're all about observing its physical manifestation in the real world.
That's truly remarkable. It really is like finding a weak point in the very fabric of the physical construction of the safe rather than guessing the combination. Now, the paper mentions two distinct flavors of these side channel attacks, non-profiled and profiled. What's the practical difference for an attacker, and why is that distinction crucial for understanding this X-DeepSCA breakthrough?
The distinction is absolutely crucial, yeah. First, we have non-profiled attacks. Techniques like differential power analysis, DPA, and correlational power analysis, CPA, fall into this category. They don't require the attacker to have an identical training device beforehand. Instead, the attacker directly analyzes the leakage from the target device itself. They collect many power traces, those recordings of power consumption over time, and then use sophisticated statistical methods to find correlations between the observed power fluctuations and potential Q values. These are well-established techniques, but they often require a large number of traces and significant computational effort directly on the target device to extract the key. The paper notes they can take a few minutes to break a device.
A few minutes still sounds pretty fast, especially for extracting a secret key. What makes a few minutes something that, well, needed to be improved upon? Is it about scale or...
That's an excellent point. While minutes might be acceptable for, say, a one-off target, consider scenarios like a production line for IoT devices, or maybe a rapid-fire attack against multiple devices in a very short window. For certain high-stakes applications, reducing that time down to seconds or even milliseconds makes the attack far more practical and scalable. It also lowers the window of opportunity for the device to potentially detect or react to an ongoing attack. And this is precisely where profiled attacks come in, which is what X-DeepSCA is built upon. Profiled attacks are typically much faster and more efficient during the actual attack phase, but they come with a different set of requirements up front. They involve two distinct stages.
Okay, 2 stages. What are they?
Right. Stage 1 is the profiling phase. Here, the attacker first needs access to an identical device. Or, ideally, as we'll see with X-DeepSCA, multiple identical devices. They then collect a vast amount of traces of this leakage data, while systematically varying parts of the cryptographic key, often focusing on just a single subkey byte at a time. The goal here is to build a highly detailed model, essentially a statistical profile, that links specific leakage patterns to specific subkey values. Think of it as creating a comprehensive signature dictionary for every possible key byte value on that particular type of device. This phase is resource intensive, sure, but it's done offline before the actual attack. Stage 2 is the attack stage. Once this model is meticulously built and fine-tuned, the attacker then uses it to classify subkeys on the actual target device under attack. Because the model is pre-trained and highly precise, it often requires far fewer traces from the target device, sometimes even just one single trace to infer the secret key. This makes the actual attack phase incredibly rapid.
So it's like building an incredibly detailed fingerprint catalog of how every single key operation looks on a specific device model, then using that catalog to quickly identify the key on a new identical device. You're front-loading a lot of the effort into that profiling phase to make the actual attack almost instantaneous.
Precisely. That's a great way to describe it. You shift much of the heavy lifting to the profiling phase. This makes the actual attack much faster and more efficient if, and this is a big if, your model is accurate and robust enough. And this is exactly where machine learning and, more recently, deep learning come into play, because they radically enhance the goodness, the predictive power of that model.
Ah, the plot thickens. Okay, we're talking about AI here, so I assume this is where the deep learning part of X-DeepSCA comes in. How has that changed the game for side channel analysis? It sounds like we're moving from older statistical methods to something much more powerful.
Oh, deep learning has been a complete game changer for profiled side-channel attacks. Absolutely. Historically, even with profiles attacks, building these leakage models required extensive statistical analysis and, frankly, significant expert knowledge. You needed a specialist, someone who really understood the hardware and the statistics, to identify the specific points in the power traces that actually leaked information, what we call points of interest. This was often a manual, tedious, and highly specialized process, prone to human error and limitations.
Right. Sounds like finding a needle in a haystack manually.
Exactly. Then in recent years, machine learning techniques like support vector machines, SVMs, self-organizing maps, SOMs, and random forests were applied to profiled SCA. These showed significant success in automating parts of this process, making it less reliant on that deep human expertise. But the real breakthrough, the one that truly paved the way for X-DeepSCA, came around 2017 with research by Cogley and others. They introduced deep learning, specifically convolutional neural networks, CNNs, for an end-to-end profiling strategy. What's truly fascinating here is that deep learning automates so much of that feature extraction that was previously manual and expert-driven. The network can learn incredibly complex and subtle patterns in the raw leakage data itself without needing explicit guidance on where exactly to look. It can even handle tricky issues like trace misalignments, where power traces don't perfectly line up in time, which was a common headache in traditional SCA. As the dimensions of data increase, which they certainly do in high-resolution power traces, deep learning becomes even more prominent because of its inherent ability to process vast amounts of noisy, complex data effectively.
That makes perfect sense. And AI can sift through massive amounts of data and spot patterns that a human eye or even traditional statistical methods might entirely miss, especially when those patterns are incredibly subtle or spread across different parts of the signal. But there was a crucial limitation, wasn't there? With all of this deep learning SCA research before X-DeepSCA, something fundamental that it couldn't quite crack.
Absolutely, and this is the critical point that X-DeepSCA directly addresses. It's the key problem they solved. Up until this work, as the paper states pretty clearly, all the previous works till date have focused on evaluating and improving the attack on the same device which has been used to train the neural network, end quote. This was the inherent Achilles heel of deep learning SCA up to that point. You could train a phenomenal model, maybe one that could crack keys almost instantly on that specific device you profiled. But its ability to generalize that learning to a different, albeit supposedly identical model device was severely limited. The ability to transfer that learned knowledge, that fingerprint catalog, to a brand new device was the missing piece. It prevented deep learning SCA from becoming a truly widespread and, frankly, scalable threat. And that, as you hinted, is precisely where X-DeepSCA changes everything. Hashtag the cross-device challenge. Why this was so hard.
Okay, so this is where it gets really interesting and, yeah, quite counterintuitive.
Yeah.
If deep learning is so incredibly good at learning complex patterns from data, why couldn't we just train a model on one specific smart thermostat, for example, and then use it to attack any other identical smart thermostat off the shelf? What was the fundamental obstacle here that previous deep learning models couldn't overcome to achieve this cross-device generalization?
That's an excellent question, and it's the core problem that X-DeepSCA set out to solve. The challenge lies in something the researchers call inter-device variation versus inter-key variation. The researchers illustrated this really powerfully in Figure 1A of their paper. They measured the absolute difference of average traces for two distinct scenarios to highlight the problem. Scenario 1, inter-key variation. That's represented by the green curve in Figure 1A. This shows how much the power traces vary when the same physical device processes data with different cryptographic keys. This is the variation that we want the deep learning model to distinguish the subtle shifts that indicate a different key byte is being used. This is the signal we're trying to detect. Scenario 2, inter-device variation. That's the red plot in Figure 1A. This shows how much the power traces vary when different physical devices, even supposedly identical models, like two separate microcontrollers, fresh off the same assembly line process data with the exact same cryptographic key. This is essentially the noise or the uniqueness of each individual device's electrical signature.
Wow. So the revelation from that figure is that the mean of device-to-device variations of the power traces is significantly higher than the mean of key-to-key class variations for one device. Okay. That is truly counterintuitive. You're saying a device's accent or fingerprint is more distinct from another identical device than the subtle changes in its own operation for different keys. How is that even possible? What does that tell us about manufacturing precision?
It's a testament to the incredibly subtle and often unpredictable world of silicon manufacturing, isn't it? Even seemingly identical chips roll off the production line with microscopic variations. These aren't defects necessarily, just tiny differences. They can stem from slight imperfections in the semiconductor fabrication process, maybe minute differences in doping concentrations, tiny variations in gate sizes, or even subtle internal wiring discrepancies, things at the nanometer scale. These minute physical differences create a unique electrical signature, an accent, as you put it, for each device. This accent often manifests as a baseline noise floor or subtle shifts in the overall power trace shape that are surprisingly stronger than the actual data-dependent leakage we're trying to exploit for the key. So what this tells us is that the inherent manufacturing variations act as a very strong source of noise from the perspective of a deep learning model trying to find the key-related signal.
Okay, that makes more sense now.
This is the crucial hurdle. Imagine trying to identify a specific word being spoken by analyzing subtle inflections in someone's voice. If every speaker has a completely unique accent that's consistently louder and more distinct than the inflections you're trying to hear, it becomes incredibly difficult to generalize your understanding from one speaker to the next. A deep learning model, if trained only on one device, tends to overfit to that specific device's unique noise and leakage profile. It learns the device's quirks, its accent. Maybe better than it learns the fundamental underlying patterns of key operations that should be common across all devices of that type.
And the researchers visually demonstrated this overfitting problem with confusion matrices in Figure 1B of their paper, right? Can you walk us through what those matrices showed? They sound like a great way to quickly grasp the problem visually.
Absolutely. Confusion matrices are excellent visual tools for understanding how well a classification model is performing, especially when it have many classes, like our 256 possible key bytes. So what they did was train a deep neural network, a DNN, on data from one device, let's call it TR1. Then, when they tested this DNN on new data from the same device, TR1, the confusion matrix showed mostly bright red dots precisely aligned along the diagonal. This is the ideal scenario. It indicates the DNN performed very well, accurately classifying unseen test traces from its own training device. The predictions aligned almost perfectly with the target key byte classes. High accuracy.
Okay, so it worked great on the device it trained on. What happened next?
Right. But then, when that exact same DNN, still trained only on TR1, was then tested on D1, a different, unseen device of the same model, the matrix became scattered. A mess, really. Red dots appeared all off the diagonal. This indicated that the model was frequently predicting the wrong key byte. It simply couldn't generalize its knowledge from TR1 to D1.
So the conclusion from this visual proof was incredibly stark. Training with one profiling device overfits to that particular device leakage and may not be able to generalize well to other devices. This was the critical hurdle X-DeepSCA needed to overcome to make deep learning-based side-channel attacks truly practical and scalable against devices you haven't profiled yourself.
Precisely. And if we connect this to the bigger picture, this explains why previous machine learning-based works hadn't really focused on cross-device attacks using deep learning. They were essentially stuck on this same device problem. While there were some cross-device template-based attacks using older statistical methods, things like principal component analysis, PCA, or linear discriminant analysis, LDA, maybe even some multi-device profiling using statistical template analysis, none had successfully achieved a robust deep learning-based cross-device attack. Deep learning's raw power for pattern recognition was effectively being confounded by the inherent physical variations between devices, which, as we saw, could overshadow the actual key-dependent leakage signal.
So the community recognized the cross-device problem, and some statistical methods had made inroads, but deep learning, despite its revolutionary advancements elsewhere, hadn't provided a solid solution for cross-device generalization until this paper. That really sets the stage for the innovation here. What specific encryption target were they going after in this research? And how did they even get the necessary data for such a novel multi-device problem? Did they have to build it themselves?
Yes, they did. The attacks in this work specifically focus on breaking the first key byte of the AES-128 encryption engine. This is a common and established practice in side-channel analysis research. The logic is, if you can successfully demonstrate breaking one byte of the key reliably, the techniques can often be scaled or adapted to break the entire key. It's about proving the feasibility and power of the attack against a critical component first.
Makes sense. Focus on one piece first.
Exactly. And for their leakage model, they use the identity ID model for 256 classification. This means the deep neural network was designed to directly classify the leakage into one of 256 possible byte values from 0 to 255. This is a more direct and often more challenging classification task than, for instance, using the Hamming-Wade HW model. The HW model only requires a 9-class classification, as it just tries to predict the number of 1 bits in a byte from 0 to 8, rather than the byte's exact value. The ID model provides a much finer-grained and thus more difficult classification target. More informative if you can get it right.
So they went for the harder, more direct approach.
They did. And this leads us to another practical and frankly quite significant challenge they faced: data availability. Existing public datasets for side-channel analysis, like the popular DPA v4 dataset or the newer ASCAD database, well, they didn't contain traces from multiple different devices captured in a way suitable for this specific kind of cross-device research. No existing dataset was designed to help train a model to generalize across devices like this. So the researchers had to literally build a new database by capturing traces from multiple devices using the ChipWhisperer platform. It's a popular open-source tool for this kind of work. Figure 2 in their paper visually illustrates their setup, where they meticulously captured power traces from multiple identical Atmega microcontroller devices. They designated a set of devices for training, TR1, TR2, TR3, TR4, and a separate, entirely distinct set for testing, D1, D2, D3, D4. This ensured a rigorous evaluation of their cross-device capabilities, avoiding any data leakage between training and testing.
That truly highlights a practical challenge inherent in groundbreaking research, doesn't it? Sometimes, to solve a truly novel problem, you can't just rely on existing resources. You have to build your own data infrastructure from scratch because the problem you're trying to solve is so new that existing resources don't quite fit the bill. They literally had to create the data to prove their point, which speaks volumes about the effort involved.
Yeah.
Hashtag X-DeepSCA unleashed how it works and its power.
So, given that significant overfitting problem we just discussed, where a model trained on one device simply couldn't generalize its attack to another device, the core innovation of X-DeepSCA is actually quite elegant in its solution. The key insight is to explicitly address the inter-device variation problem head-on. How? By training the deep neural network with traces augmented from multiple profiling devices. Instead of just using one training device like TR1, they strategically used TR1, TR2, TR3, and TR4, pooling their data together.
Ah, okay.
Yeah.
So instead of just teaching the AI one accent of how a key operation sounds on a device, you teach it a whole range of accents for the same word, if you will. This would then make it robust enough to understand a new speaker, a new device it's never heard before, because it's learned the commonalities across all those variations. It makes perfect intuitive sense once you hear it explained like that.
You've got it exactly. That's the core idea. This multi-device training strategy forces the DNN to learn the underlying device-agnostic leakage patterns related to the actual key operation, rather than merely memorizing the unique noise and quirks of a single device. It essentially teaches the network to extract the essential information, the signal that's common across all devices of that model, despite their individual manufacturing variations. By exposing the network to these diverse accents during training, it learns to filter out the device-specific noise and focus on the subtle, consistent signal of the cryptographic operation itself.
Brilliant. Let's get into the brain behind the attack then. What does the X-DeepSCA deep neural network architecture, as shown in Figure 3, actually look like? What kind of network are we talking about, and what are its key components?
Okay, so the X-DeepSCA model uses a fully connected, FC deep neural network, DNN, sometimes called the multi-layer perceptron or MLP. The researchers specifically note that because their captured traces are time synchronized, meaning all the data points from different traces align precisely in time, a more complex idioparum. Convolutional neural network, CNN, wasn't strictly necessary for the input layer. This allowed for a simpler yet highly effective network architecture. If the traces weren't aligned, CNN would likely be preferred for its ability to learn features regardless of their exact position in time. But here, alignment simplified things.
Okay, so a fully connected DNN. Let's break down its components. Input first.
Right. Input layer. Originally, the AES-128 encryption operation they captured produced 3,000 time samples per power trace. That's quite a bit of data for each encryption. However, through experimentation, they found that the DNN could learn accurately and efficiently from just the first 200 time samples. That's where the most critical leakage related to the key seemed to occur. So to optimize complexity and training time while ensuring all relevant information was still captured, they ultimately fed only the first 500 time samples from each power trace into the network. This shows a smart approach to data efficiency, focusing the network's resources on the most informative parts of the signal.
That's pretty insightful. The network quickly figured out where the most juicy bits of information were in all that data without needing to process the entire 3,000 samples. Like finding the right page in a book without reading the whole thing. Efficient.
Precisely. Then we move into the crucial hidden layers. First, fully connected hidden layer. This layer has 200 neurons. The researchers carefully determined this number, finding that increasing the number of hidden neurons beyond this could actually lead to overfitting, where the model becomes too specialized to the training data and struggles to generalize. Following this layer are several crucial regularization and activation techniques, which are really important for making this work robustly. Batch normalization. This is critical, especially when dealing with subtle signals buried in noise and high variability, like our inter-device variations. Imagine trying to train a model to recognize faces, but the lighting is wildly different in every photo. Batch normalization essentially normalizes the input to each layer, ensuring a consistent lighting or scale for the network as it learns. This stabilizes and speeds up training by preventing something called internal covariate shift, where the distribution of network activations changes during training. It also provides a form of regularization by adding a slight noise effect, preventing the model from getting bogged down by wildly fluctuating data scales. Without it, the network might really struggle to find those subtle key patterns amidst the louder device variations. Rectified linear unit, or LU activation. This is a common nonlinear activation function, chosen for good reason. It simply outputs the input directly if it's positive and zero otherwise. This nonlinearity is essential because it allows the network to learn complex nonlinear mappings between its inputs and outputs. That's absolutely necessary for identifying the subtle, often nonlinear leakage patterns in power traces. Without nonlinear activation, the network would essentially just be a linear model, incapable of learning anything truly complex. Dropout layer. This is a powerful regularization trick, specifically for fighting that overfitting problem we talked about. Think of it like forming multiple smaller, slightly different expert teams within the network to solve the same problem. During training, a random percentage here, typically between 10% and 30% of neurons in this layer, are temporarily switched off or dropped out, ignored. This forces the remaining neurons to work harder and learn more independently, preventing them from becoming overly reliant on any single feature or from co-adapting too much to the quirks of a specific training device. In our case, it's crucial for ensuring the model learns the fundamental leakage patterns related to the key operation, not just the accent of one particular training device.
Okay, batch norm, ReLU, dropout. Standard but crucial tools for deep learning. What about the next layer?
Second fully connected hidden layer. This layer is similar to the first, also with 200 neurons, but notably, the paper mentions it's without the dropout layer applied directly after it. This design choice likely helps maintain the learned representations while allowing the network to converge effectively towards the end. Output layer. This final layer has 256 neurons. This number is specifically chosen because it corresponds exactly to the 256 possible values of a single key byte, from 0 to 255, softmax function. This function is applied to the output layer. It takes the raw outputs, logits from the 256 neurons, and converts them into a probability distribution. Essentially, it ensures that all 256 outputs sum to 1. This allows the network to predict the correct key byte by simply identifying the output neuron with the highest probability.
And how was this network actually trained? What were the settings?
Right, the training details. They used categorical cross-entropy as the loss function. This is standard for multi-class classification problems like this one, 256 classes. It measures how far off the network's probability predictions are from the true actual key byte used during that trace capture. This loss was optimized using the ATOM algorithm. ATOM is a very popular and highly efficient method for adjusting the network's internal weights during training. It's known for its adaptive learning rate capabilities, which helps it converge quickly and reliably, and the use of batch size of 32. This means the network processed 32 power traces at a time before calculating the loss and updating its weights.
Got it. So even with a great architecture like this, sometimes the settings or hyperparameters for the AI model can make or break its performance, right? It's like tuning a high-performance engine. Even the best engine won't run optimally without the right fuel-air mix and timing adjusted correctly.
That's an absolutely critical point, yes. And it's especially important here for a 256 class classifier, which is significantly more difficult to design and train accurately than, say, a simpler 9-class classifier like the Hamming-Weight model we mentioned earlier. Proper choice of hyperparameters is essential to prevent two major pitfalls. Overfitting, where the model essentially just memorizes the training data but can't generalize to new unseen data like other devices, or underfitting, where it hasn't learned enough from the training data at all.
It's a very delicate balance.
So what do they find when tuning these hyperparameters? Figure 4 on the paper addresses this, right? Exactly. The researchers conducted extensive experiments to find the optimal settings, as shown in Figure 4. Their key findings regarding these hyperparameters were quite interesting. Learning rate, Figure 4a. This controls how much the network's weights are adjusted with each step during training. Too high, and it might overshoot the best solution. Too low, and it might take forever to train or get stuck. They found that a learning rate of around 0.01 provides the maximum test accuracy. Interestingly, they observed that higher learning rates actually led to overfitting. This happens because the model would take too large steps in adjusting its weights, effectively jumping past the optimal solution and failing to settle into a well-generalized state that works across different devices. A lower, more controlled learning rate allowed it to converge more effectively. Dropout, Figure 4b. This is where it gets really fascinating. Surprisingly, they found that lower dropout rates, and even no dropout in some experiments, showed high accuracy. The researchers theorize, and this is quite insightful, that this is because the data gathered from the real-world devices has sufficient electronic noise inherent in the power traces themselves. This natural electronic noise from the physical devices already acts as a form of regularization, inadvertently helping to prevent overfitting. It's like the real world was already adding a bit of helpful randomness that helped the network generalize. However, they also noted that dropout, more than 30%, led to reduced classification accuracy. So too much artificial dropout prevented the network from learning effectively for the actual signal amidst the noise.
Wow, so the noise from the actual device was inadvertently helping to regularize the model, almost like a happy accident of the physics involved. That's a truly fascinating insight into how these complex systems interact. How did they feed data into this finely tuned machine for training then? What was their specific data strategy to maximize the effect of that multi-device training?
Yeah, their data strategy was key to the X-DeepSCA innovation. For most of their experiments, they adopted a strategic approach. 10 K traces from each of the 4 devices, TR1, TR2, TR3, and TR4, were augmented together for training. This means they didn't train on TR1 first, then TR2, and so on. No, they pooled the data from all 4 distinct devices into one large training set right from the start. This created a rich, diverse data set that explicitly included the inter-device variations the model needed to learn to generalize over, and to ensure they were building a robust model, and, crucially, to monitor for overfitting during the actual training process, 20% of the total number of traces were kept for validation. This validation set wasn't used for updating the model's weights, it was just used to check performance periodically. It allowed them to gauge how well the model was generalizing to data it hadn't explicitly been trained on, but which still came from the same pool of training devices, TR14, providing an unbiased estimate of its performance during development and helping them know when to stop training.
Okay, so now that the X-DeepSCA model is built and trained using this multi-device data and careful tuning, let's talk results. How did the single-trace X-DeepSCA attack perform, especially on those previously challenging new devices? Did it work?
Did it ever? The performance was remarkably strong and converged very quickly, as illustrated clearly in Figure 5. The DNN model achieved an accuracy of 99.9% within just 25 epochs. Remember, epoch is one complete pass of the training beta through the network. This rapid convergence to such incredibly high accuracy demonstrates its impressive learning capability from those diverse device traces. Furthermore, both the training loss and the validation loss approach to zero, indicating successful learning without significant overfitting. It's also worth noting, as a technical aside, that the validation loss was slightly lower than the training loss in their plot. This is actually expected behavior because the dropout layer is active only during training, making training slightly harder, but is turned off during validation, which then sees the full network perform slightly better on data it's generally learned well.
Okay, 99.9% accuracy in 25-bit box is seriously fast learning. But the real test is generalization, right? How did it do on totally new devices?
Exactly, that's the million-dollar question. So they tested this trained X-DeepSCA model on a separate set of entirely unseen devices, D1 through D4. These devices played no part in training or validation. The results, shown in Figure 6, were scalable and profoundly impressive, demonstrating true cross-device capability. The model achieves 99% accuracy with 40K training traces in total. That means 10,000 traces from each of the 4 training devices, TR1 through TR4. And it achieved an even more astounding 99.9% accuracy with 200K training traces in total, again, drawn equally from TR1 through TR4, so 50K traces from each.
Wow. So if you feed it enough examples from different devices, it truly learns to generalize. It becomes incredibly potent against any new similar device it encounters. It doesn't get confused by a new device's unique accent anymore. It understands the universal language of the key operations. That's a huge leap from previous methods, a true breakthrough in practical application.
You summarized it perfectly. That's exactly the takeaway. And the visual proof of this generalization is absolutely compelling in Figure 7. That figure shows the confusion matrices for each of the test devices, D1, D2, D3, D4, when the model was trained on 40K traces. Even with only 40K training traces, these matrices clearly showed that at most 3 key bytes out of the 256 were misclassified for each device. The vast majority of predictions were spot on, right along the diagonal. This overwhelmingly confirmed the high overall accuracy and, most importantly, the model's ability to generalize its attack knowledge to completely new, unseen devices, which, again, was the core challenge it set out to solve.
And Figure 8 really hammers home the power of augmentation, doesn't it? That multi-device training approach you talked about earlier, that seems to be the absolute core innovation that makes this whole thing work.
It absolutely does. Yeah, Figure 8 is perhaps the most critical result for understanding why X-DeepSCA works so well. This figure directly addresses that fundamental cross-device problem we discussed. When the deep neural network was trained with only one training device, for instance, just using traces from TR1, the accuracy when tested on a new device, say D1, dropped significantly down to around 80%. This is that overfitting problem laid bare. The model had become too specialized to the unique characteristics, the accent of TR1, but by augmenting traces from all the 4 training devices, essentially training it on a much richer, more diverse set of accents, the accuracy soared dramatically to around 99%. This is the linchpin of X-DeepSCA's success. It unequivocally shows that without this multi-device training, the deep learning attack would be far less practical and effective in a real-world scenario where you don't control the target device's specific instance. The augmentation is what allows the DNN to learn a more robust device-independent leakage model, making it a truly formidable cross-device attack. Hashtag Beyond Average, the Ntrace X-DeepSCA advantage.
Okay, so the overall average accuracy is astounding, greater than 99.9%. That sounds almost perfect and incredibly fast with just a single trace. But does that mean every single one of the 256 possible key bytes can be cracked with just one listen, every single time? Because in cybersecurity, often, success hinges on the weakest link, right? Not just the average performance. You need 100% confidence, ideally, to truly recover a secret key.
That's a critical distinction, yeah, and you've hit on a very important point for practical attacks. Absolutely right. While the average accuracy is incredibly high, a deeper analysis is always needed, because an adversary typically needs to crack every byte of the key with high confidence, not just most of them. So the researchers looked at the individual key byte class accuracy distribution in Figure 9a and 9b. They specifically focused on test device D4 for this analysis. Why D4? Because, interestingly, this device presented the lowest average accuracy among the test devices, though still very high. So analyzing D4 represents the worst-case scenario for an attacker trying to break the key.
Okay, looking at the hardest case. Smart.
Exactly. And to quantify the uncertainty for individual key bytes, they introduced a unique measure they called entropy, meet target, for the X-DeepSCA attack. It's defined in Equation 1 in their paper. This measure essentially quantifies the separation or the gap between the probability the model assigns to the correct class prediction and the maximum probability assigns to any incorrect class misprediction for any given key byte. In simpler terms, it tells us how ambiguous or uncertain the model is about a particular key byte. If the correct answer and a wrong answer have similar probabilities according to the model, the entropy is high and the model is effectively unsure, even if the correct one is slightly higher.
Okay, so what did this entropy measure reveal in Figure 9?
The insights from Figure 9 are quite revealing about the benefits of multi-device training, even for confidence. One-device training, Figure 9a. When the model was trained on only one device for some specific key bytes, the correct class accuracy, shown as the black plot, and the maximum mispredicted class percentage, the red plot, actually overlapped, or came very close. This indicates very high entropy for those bytes. It means the model was very uncertain for these specific key values, and relying on a single trace might fail or provide an ambiguous result, leaving the attacker guessing between two or more possibilities. Four-device training, Figure 9b. Critically, training with 4 devices has significantly lower entropy, key target, compared to one-device training. There's a much clearer separation, a wider gap between the correct predictions, black plot, and the highest mispredictions, red plot, across almost all key bytes. This indicates much higher confidence for the model's predictions.
So multi-device training not only improves average accuracy, but also boosts the confidence for individual key bytes.
Precisely. However, even with the impressive 99% average accuracy achieved with 4-device training, the paper honestly notes that the minimum accuracy of a few key bytes drops below 80%. So while most key bytes were easily cracked with near certainty using just a single trace, a small subset remained stubbornly elusive, where the model had less than 80% confidence in its single trace prediction.
So even with the fantastic overall accuracy and cross-device generalization, for a handful of these stubborn key bytes, a single trace might still leave you guessing, or worse, lead to a wrong conclusion. You definitely don't want to be guessing when trying to recover a secret cryptographic key.
Exactly right. The conclusion was clear. Hence, although the single trace attack will succeed on most key bytes, it may not work for a few key bytes, and a multi-trace attack is required. To reliably crack all key bytes with high confidence, the researchers propose an elegant and highly practical solution, the N-trace X-DeepSCA attack, which uses simple majority voting.
Okay, N-trace X-DeepSCA attack with majority voting. So it's like if one person in a crowd is hard to understand, you just ask a few more people nearby, and eventually the consistent answer from the majority gives you the confidence you need. You don't need hundreds of extra traces, just a few more listens to confirm the answer for those tricky bytes.
That's a perfect analogy for it. Yes. Instead of relying on a single prediction from just one trace, which might be ambiguous for those low accuracy bytes, they collect N traces for the same key byte. Then they simply take the most frequent prediction among those N traces. It's straightforward. If the model predicted the key byte is 0xA 5 times and 0xCD only twice out of, say, 10 traces, then 0xAB wins the vote. The paper even provides a mathematical derivation, equation 2, to calculate the probability of success for this majority voting approach. It's valid for N or 3 traces. It models how the confidence grows rapidly with repeated observations, even if the single trace accuracy isn't perfect.
And how effective is this N-trace approach? How many extra traces do you need?
The power of this approach is vividly demonstrated in Figure 10. Even for the lowest accuracy key byte found in their experiments, the one that had only 70% accuracy, P1.7, with a single trace, the N-trace X-DeepSCA attack achieves a success probability of 99.9% with NA10 encryptions. This means that even for the absolute most challenging key bytes, those that the single trace attack struggled with the most, an attacker only needs to observe the device's operation a maximum of 10 times to be virtually certain, 99.9% probability, of the correct key byte value.
Wow, that makes the attack incredibly practical and robust. It's about achieving high confidence across all possible key values, not just on average. It closes that small gap of uncertainty, turning a highly effective attack into a near-guaranteed one with minimal extra effort. 10 extra observations is practically trivial for an attacker given the payoff of getting a secret key. #tag speed and resilience X-DeepSCA's real-world impact.
This naturally raises an important question for real-world applicability. How well does the sophisticated X-DeepSCA attack work in noisy, real-world environments? We've talked about device variation, but what about external noise? Signal-to-noise ratio, or SNR, is a crucial factor in practical side-channel attacks. Because real devices aren't typically running in pristine, shielded lab conditions. They're often surrounded by electrical interference from other components on the same board, power supply fluctuations, environmental noise, and other forms of noise that can obscure that subtle leakage signal we're trying to measure.
Right. If the signal is clear, it's one thing, but if it's completely buried in static interference, can the deep learning still pull out the key effectively, or does the noise become too overwhelming?
That's precisely what they investigated. And Figure 11A shows the performance of the N-trace attack under varying SNR levels. The resilience of X-DeepSCA to noise is actually quite impressive. In a high SNR environment, 20 dB, where the leakage signal is relatively clear compared to the background noise, averaging less than 10 traces is sufficient to achieve 99.9% accuracy. That's incredibly fast and efficient, basically confirming the N10 result from before in good conditions. For a medium SNR, 10 dB, which is perhaps the more common real-world scenario with moderate noise, it requires around 100 traces to average to reach that 99.9% confidence. Still very manageable for an attacker. And even in a low SNR environment, 0 dB, where the signal from the cryptographic operation is almost completely buried in noise, literally as strong as the noise itself, making it visually indistinguishable on an oscilloscope that the N-trace X-DeepSCA attack can still succeed. Though, as expected, it requires more data. Around 1,000 traces to average to hit that 99.9% success probability.
Okay, wow. So even when the signal from the device is almost completely buried in noise, where it's practically indistinguishable to the human eye, the deep learning approach combined with N-trace averaging can still work. It just needs a bit more data to effectively filter out the static and extract those meaningful patterns. That speaks volumes about its resilience and robustness in challenging realistic conditions.
Indeed, it does. It demonstrates the deep learning model's remarkable ability to effectively denoise and extract subtle features, even from very challenging, noisy data streams. It's learning to find that needle in the haystack, even when the haystacks are constantly changing shape and the needles are whispering very quietly. But perhaps the most striking finding regarding real-world impact comes from Figure 11b. This figure dramatically compares the efficiency of X-DeepSCA to traditional correlational power analysis, or CPA, which is a standard non-profiled technique.
And the key metric here is minimum traces to disclosure, or MTD, right? Basically, the number of traces needed to successfully retrieve the key. The fewer traces needed, the faster and more effective the attack. Which means less time, less risk for the attacker, and a wider window of vulnerability for the devices.
Exactly. Lower MTD is better for the attacker, worse for security. And Figure 11b vividly shows that the number of traces required to retrieve the correct key byte is approximately 10 times lower than the traditional CPA attack across different SNR levels. This isn't just an incremental improvement of, say, 10 or 20%. It's an order of magnitude leap in efficiency. 10 times fewer traces needed. This translates directly to a massive speed-up in practical attack scenarios. It effectively takes attacks that might have required minutes using traditional CPA and reduces the time needed down to seconds using X-DeepSCA.
What's fascinating here is that this isn't just an incremental improvement, it's a fundamental shift in the economics practicality of side-channel attacks. It makes them far more accessible and potent for adversaries because the barrier to entry in terms of time needed, potentially specialized equipment complexity, and the amount of data collection required has been significantly lowered. This is truly a game changer for the threat landscape.
Absolutely, you've nailed it. The abstract of the paper itself explicitly states that X-DeepSCA increases the threat surface for embedded devices significantly. This isn't just a theoretical breakthrough confined to a lab. It has very real and immediate implications for the security of countless devices that permeate our daily lives.
So this isn't just a theoretical breakthrough for academics publishing papers. It means that things like smart home devices controlling our security systems, maybe IoT sensors monitoring critical infrastructure, medical implants maintaining health, or even critical electronic control units, ECUs, in our cars, all of which rely heavily on embedded cryptography. They could be vulnerable in new and, crucially, much more accessible ways now. What does this all mean for the manufacturers and security experts who are designing these devices right now? How should they react to this kind of advanced cross-device threat that's also much faster?
It means countermeasures need to evolve, and they need to evolve rapidly. We can no longer operate under the assumption that merely implementing a mathematically secure algorithm in software is sufficient to protect sensitive data on embedded devices. It's clearly not enough anymore. The focus must broaden significantly beyond just the logical security of the code itself. Physical security measures, things that prevent unauthorized physical access or tampering with the device, become even more critical because an attacker still generally needs physical proximity to collect these side-channel traces, power, or EM.
Right, physical access is often still required. But what about defenses built into the device itself?
Yes. Beyond physical access controls, there's intensified research and deployment needed for robust active countermeasures within the hardware and software. This includes noise injection masking, deliberately introducing controlled electrical noise or obfuscation into the power consumption or electromagnetic emissions of the device during cryptographic operations. This is designed specifically to obscure or mask the side-channel leakages that an attacker might try to exploit. Imagine trying to eavesdrop on a conversation while someone is deliberately playing loud static right next to it. Hardware design changes. Fundamentally, new hardware designs that actively suppress these physical emanations from the chip itself will become paramount. This could include things like specialized shielding built into the chip package, using differential logic, where two inverse signals run in parallel, theoretically canceling out external leakage, or perhaps asynchronous circuit designs that don't rely on a global clock signal, making timing attacks much harder. It forces a truly holistic reevaluation of security right from the ground up. It requires integrating physical security, hardware design choices, and cryptographic implementation security in ways that perhaps haven't been done systematically enough in the past.
And the researchers themselves also point to future work, ways to make X-DeepSCA potentially even stronger. What are they looking at next to refine this already potent attack?
Yeah, they suggest that the efficacy of X-DeepSCA could be further improved. How? By ensuring that the accuracy of each key byte and the mispredicted classes for that key byte are uniformly distributed. What does that mean? Essentially, the goal is to minimize bias in the DNN's misclassification behavior. So when the model does make a mistake on a key byte prediction, it does so more randomly across all the possible wrong answers, rather than consistently favoring just one or two specific incorrect guesses, which is what high entropy indicates. If they could achieve this more uniform misprediction profile, it would likely further lower the number of traces N required for a successful N-trace attack using majority voting. It could potentially reduce N even below the current ND10 needed for the most stubborn key bytes in their tests. This would make an already potent and efficient attack even more devastatingly precise and quick. Hashtag tag outro Gale.
We've covered a massive amount of ground today in this deep dive into X-DeepSCA. It's really quite something. We've seen how this novel cross-device deep learning side-channel attack has achieved, well, unprecedented success. By training a deep neural network on power traces meticulously collected from multiple physical devices, it cleverly overcomes that critical challenge of inter-device variations, those unique accents of each chip. This leads to an astounding over 99.9% average accuracy on entirely new, unseen devices. We learned about the N-trace attack, which, by using simple majority voting on just a handful of extra observations, guarantees over 99.9% confidence, even for the most stubborn key bytes, requiring a maximum of just 10 encryptions in their tests. And perhaps most strikingly, X-DeepSCA dramatically accelerates the attack time from minutes potentially down to mere seconds. It requires roughly 10 times fewer traces than traditional methods, even in noisy real-world environments.
What's fascinating here really is the continuous interplay, this ongoing arms race between developing new, mathematically robust cryptographic techniques and discovering ingenious new ways to circumvent their physical implementations on hardware. This work serves as a stark reminder that security is a profoundly holistic challenge. It requires vigilance and innovation at every single layer, from the abstract mathematical algorithms right down to the very electrons flowing through the silicon of our devices. It forces us to think about security not just as a software problem, which is often the focus, but as an inherent hardware and physical implementation problem as well. They're deeply intertwined.
Indeed. This deep dive isn't just about a specific attack. It's a crucial peek into that ongoing arms race in digital security. And as our devices become more ubiquitous, more interconnected, embedded in every aspect of our lives, from personal health monitoring to global infrastructure control, understanding these subtle physical vulnerabilities becomes absolutely paramount. It's not optional anymore.
It truly does. We're moving into an era where potentially every tiny hum, every power flicker, every slight thermal shift or electromagnetic emission could potentially be a telltale sign of a secret being revealed. The adversary's toolkit is becoming incredibly sophisticated, leveraging AI in ways we're only beginning to fully grasp.
So consider the profound implications for the devices you use every single day. From your smartwatch tracking your most sensitive health data, to your car's navigation system, to the countless IoT sensors that might be deployed around your home, your workplace, your city. If a secret key, the very foundation of their security, can be extracted in seconds by merely listening to a device's power consumption, even across different device instances, How will this fundamental shift in attack capabilities reshape the design and manufacturing of future embedded systems? What new silent shields, what entirely novel hardware and software countermeasures will need to be developed to counteract these sophisticated silent eavesdroppers? It's a huge question, and one that hardware designers, cryptographers, and cybersecurity researchers will definitely be grappling with for years to come.